Hello everyone, my name is Chen, a PhD student from National University of Singapore. Today I'm going to present our paper, Deep AM/FM Toolkit for Automatic Dialogue Evaluation. Here is the presentation outline. Firstly, I will introduce the research background of the paper and talk a little bit more of the original AM/FM framework based on traditional machine learning techniques and the challenges faced by the vanilla AM/FM. Then I will introduce our deep AM/FM framework and talk about how it helps address the limitations leverage deep learning techniques. For the experimental part, I will discuss in detail the dataset we use to train our models, as well as the human evaluation dataset we use to examine the effectiveness of deep learning-based AM/FM. Following that, it is the implementation details, then the results and analysis, and finally, the conclusion and the future plan. Let's look at the research background of the paper. In recent years, there is growing interest in building open domain generative dialogue models. The evaluation metric has become the long-term bottleneck to the advancement of this field. Effective evaluation can provide useful feedback to improve the systems, while poor metrics will mislead the research development work. Generally, two types of evaluation methods are adopted to help evaluate open domain dialogue systems. The human evaluation, which is normally in the form of questionnaire, A/B test, and real-time user interaction. However, human evaluation is expensive and cannot be easily scaled to new datasets. Hence, various automatic evaluation metrics are proposed to be used as proxies to human evaluation to assess the quality of dialogue generation models at a large scale. In automatic dialogue evaluation, there is a challenge problem called the one-to-many problem. Given a dialogue context, there may be quite a diverse number of valid responses. The effectiveness of metrics based on n-gram matching is greatly compromised by this problem. Popular metrics like BLUE aggressively penalize valid responses that are lexically different from the human written references, thus leading to poor correlation between the metrics and the human judgment. The automatic dialogue evaluation metrics can be roughly grouped into three categories: the word overlap metrics, embedding-based metrics, and model-based metrics. Here we list out some of the examples belonging to each of the category. So what is AM/FM framework? It was originally proposed in the paper Adequacy, Fluency Matrix Evaluating Machine Translation in the Continuous Space Model Framework, published on IEEE Transaction on Audio, Speech, and Language Processing in 2015. So it is a framework used to evaluate machine translation systems. The AM is called Adequacy metric, which tries to measure the semantic quality of translation system hypothesis. The FM refers to Fluency metric, which uses a language model to measure the syntactic quality of the generated system hypothesis. This framework tries to decouple the semantic and syntactic aspects of machine translation and evaluate each component individually. There are two versions of implementations. One is the cross AM/FM, and the other is a mono AM/FM. The difference between these two lies in the adequacy metric component. The cross AM directly compares the source sentence with the translated sentence in the semantic space, while the mono AM compares the translated sentence with the human written references at the target site. This framework has achieved better correlation with human judgment as compared to other popular machine translation evaluation metrics on the WMT07 evaluation dataset. Then there is a more recent paper titled Automatic Evaluation of End-to-End Dialogue Systems with Adequacy Fluency Metrics. This paper extends the original model AM/FM version to the dialogue evaluation domain, and this reference-based metric helps mitigate the one-to-many problems in dialogue evaluation, leveraging the multiple number of human written references, and has achieved state-of-the-art correlation on DSTC6 evaluation data. It is also the baseline we try to compare our deep AM/FM with. Now let's take a close look at the original implementation of AM and FM and discover some of their drawbacks. The AM score is computed as a cosine similarity between the reference sentence represented by R and the system hypothesis represented by T. The projection matrix U is learned via latent semantic indexing approach. M is the vocabulary size, and L is the dimensionality of the embedding. For the FM score, it is computed as the relative scale between the normalized log probability of the candidate and the golden reference. The probability of the sentence is estimated with an n-gram language model. So both the AM and FM score is a value between 0 and 1. The original formulation faces some of the limitations. Firstly, the latent semantic indexing approach leverages term document matrix formed with non-sequential features such as bag of words, so the contextual information in text is lost here. In addition, the SVD operation is not scalable. If the data set becomes larger, the memory may not be sufficient for conducting operation on large matrix. Finally, the n-gram language model also suffers from the well-known problem of not able to capture long-term contextual dependency. So let's dive into deep AM/FM framework. The difference between deep AM/FM and the vanilla AM/FM is that both adequacy metrics and fluency metrics are modeled with deep learning-based techniques, which helps address the aforementioned limitations. In the following slides, we will look deeper into the individual components of the framework. For the adequacy modeling, the general idea is similar to the original formulation. The AM matrix serves to assess the semantic quality of generated responses. A large pre-trained language model is chosen and fine-tuned on the dialogue training data so as to provide high-quality contextualized representation. Both the hypothesis and the reference will be mapped to continuous vector representation, and their cosine similarity is used as the AM score. The key difference here is that we will use BERT to derive sentence-level contextualized representation. The reason why we choose BERT is because the good representation power of its pre-trained model. In addition, the model can be easily adapted to different data domains for various evaluation tasks, and the next sentence prediction objective of BERT is useful for discourse level modeling. This is helpful for modeling dialogues in our case. The figure here shows the input representation of BERT as well as its pre-training objectives, the next sentence prediction, and the masked language model objective. The input, we can see two sentences in parallel that are tokenized into word piece tokens The start token is a special CLS token, and the sentence boundaries are the special SCP tokens. Each input token is represented by a concatenation of 3 types of embeddings: the token embedding, segment embedding, as well as the transformer positional embedding. We can see that some of the tokens are randomly masked and represented with token embedding called E-mask, as shown in the figure, and the network is supposed to predict the original token in a sentence. This is called the masked language model pre-training objective. In addition, the hidden representation of special CLS token is used to perform a binary classification to predict whether the second sentence is a logical continuation of the first sentence. This is called the next sentence prediction pre-training objective of BERT. The figure in this slide is a simplified version of the BERT architecture. Basically, BERT consists of transformer encoders, and its base version contains 12 layers of the encoders. When the tokenized sequence is passed through the encoders, each layer is supposed to derive hidden representation of the tokens, and the hidden state at the final layer is used for classification purpose, either for reconstructing original tokens based on the masked tokens, or for the next sentence prediction objective. Now let's see how we can derive the AM score with a pre-trained language model. Firstly, we extract the token-wise top hidden layer representation of both the existing hypothesis and the reference, and then we apply the embedding average method to obtain sentence level embedding from the individual token level embedding. After that, we compute the cosine similarity between the system hypothesis and the references. In the case of presence of multiple references, here let's consider 11 of them. The maximum cosine similarity value is kept as the individual AM score. The system level AM score is computed as an average of AM scores of all test cases. In the actual implementation, we use a dataset of 2,000 test cases. So we can see here we average the sum of AM score over 2,000 in the formula. After discussing deep AM metric, let's look at the FM metric modeling. The general idea remains the same as the original formulation. The FM metric serves to assess the syntactic quality of generated responses. We will pre-train an autoregressive language model and use the model to obtain sentence-level perplexity. This idea is based on the assumption that sentences sharing similar perplexity levels should possess similar syntactic quality. Given that human written references are syntactically sound, if a system hypothesis is close to the reference in terms of perplexity level, then the syntactic quality of the hypothesis should be okay. Here, the difference with the original formulation is the use of LSTM language model. The reason why we choose LSTM language model is because it is simple autoregressive language model to implement, and it is able to help address the problem of n-gram language model that we mentioned in the previous slides, because we need to capture the long-term contextual dependency in text. Figure 5 shows an unrolled version of the LSTM language model. We can see that for training, the input and output are the same sequence, except that the output is right-shifted by one token. At each time step, the current token input and the previous hidden state is used to generate the current step hidden state and predict the next token. The gating mechanism of LSTM is supposed to address the vanishing gradient problem associated with vanilla recurrent neural network, and hence control the information flow and return the long-term information. The slide here outlines the computation details of FM metric. In the first formula here, R represents the reference sequence. The perplexity level of R can be derived as the exponentiation of its coarse entropy. In the second formula, we divide the log of joint probability of the word sequence by n, and then we can obtain the normalized sentence level probability by taking exponentiation of the result. Given that perplexity of the sequence can be obtained by the probability of the sequence to the power of -1 over n, when we take log on both sides, we can arrive at a final formula that the normalized probability of sequence R is actually the inverse of its perplexity. Then we can derive the perplexity of R based on the first formula, given that we have a well-trained LSTM language model. So finally, the FM score is computed as the relative scale between the candidate and the reference following the final formula here. The resultant FM score is the value between 0 and 1. The closer to 1 meaning that a similar system hypothesis to a reference in terms of syntactic quality. So after talking about the formulation of deep AM/FM framework, let's take a look at the experiment. In this section, we'll look at the dataset as well as the implementation details. So the dialog dataset we use to train our deep AM/FM models are from the DSTC6 end-to-end conversational modeling track. DSTC stands for Dialogue System Technology Challenge. It is an annual research challenge for advancing the dialogue system technology. In the end-to-end conversational track of DSTC6, the training set consists of 1.7 million Twitter dialogues. The validation set contains 52.7K dialogues. We use the training set to train the deep FM model and the validation set to tune our model. And the test set contains 2,000 Twitter dialogues, which are only used for the evaluation task. For the evaluation dataset, human evaluation is conducted on the 2,000 test dialogues. There are in total 20 system submissions. Each test dialogue has 11 human written references, including the original response. Each test case is evaluated by 10 human judges on a 1 to 5 point scale. As you can see, here is an example of the test case with the dialogue context, system hypothesis, as well as 10 human ratings. So basically, we will compare our deep AM/FM score with the human scores to evaluate the effectiveness of our proposed metric. Here is some implementation details of the experiment. For AM modeling, we used BERT-based multilingual model. This is because in the Twitter data there is presence of foreign languages. Then we fine-tune the pre-trained model with dialogues of different sizes, like 10K, 20K, 50K, and 100K, to showcase that the deep learning-based model is able to handle increasing amount of data, which is an advantage against the original SVD formulation. For the FM modeling, we train LSTM language model from the scratch with the same amount of dialect data of different sizes, so ranging from 10K to 100K. As for the experimental environment, we use the TensorFlow deep learning library. All models are trained on a single GTX 2080 Ti GPU, and their training time ranging from a few hours to a few days depending on the amount of training data. Finally, here comes the result and analysis part. Let us take a look at the objective result. In table 1, we can notice that with increasing amount of data, both masking language model and the next sentence prediction accuracy increases. This indicates the power of deep learning for handling increasing amount of data. The more data we have, better model we can obtain. We can observe similar trend in table 2 as the data size increases. Generally, the perplexity level decreases for LSTM language model. As we can see that the perplexity level of LSTM language model is much lower than the n-gram counterpart, given the same amount of training data. This slide here shows the Pearson and Spearman correlation of individual AM and FM component with respect to the corresponding human judgment. We compare the deep version against the original implementation. So in table 3, we can see that the BERT 20K model outperforms the original AM SVD model in terms of both the Pearson and the Spearman correlation. However, the performance of BERT model fine-tuned with other data sets didn't perform equally well. This is the part that requires further error analysis. In table 4, we can see that the LSTM language model trained on 100K dialog data outperforms all the n-gram models in terms of both Pearson and Spearman correlation. It is worth noting that the n-gram models to compare with here are all learned with the entire training set, while the LSTM language model is only trained with part of the training data, yet it is still outperformed the n-gram counterparts. This slide shows the overall correlation results. We compare deep AM/FM against all the baseline metrics, including word overlap metrics like BLEU, METEOR, the embedding-based metrics, including skip sort and the embedding average, as well as the original AM/FM baseline. So we can see that when we give equal weights to AM and FM components, which means that lambda value is set to 0.1, we can see that the performance of a deep AM/FM are better than all the baselines in terms of both the Pearson correlation and the Spearman correlation. So this showcases the effectiveness of our proposed deep AM/FM framework. So in conclusion, we start by discussing the research problems of automatic dialogue evaluation and the limitations of the original AM/FM framework, which was intended for evaluating dialogue responses. The main contribution of the paper is the proposal of the deep version of the AM/FM framework, which has a very good correlation with human judgment. In addition, we open source the toolkit for all future automatic dialogue evaluation research, and this framework leverages state-of-the-art deep learning techniques. which helps address the problems associated with the original AM/FM model. Hence, in the future, we plan to work towards reference-free automatic dialogue evaluation, and we also intend to incorporate coherence into our evaluation framework. In addition, we will gradually move towards a holistic automatic dialogue evaluation. Now I have come to the end of my presentation, and thank you for listening.